discuss some modeling with the topic of this conference. Any type of transition. Work was done in long collaboration with Magnetic and so on, who's supposed to come to this conference, but it was Uppsala now, but we did this all together, part of the Ukrainian collaboration. Good. We discussed magnetism, better inherent correlation effect, discussed how to calculate, to model properties of magnetic materials, and then discussed just calculation. And also superconductivity is very complicated on local effects. So as I said, I like the title of this conference, Abstract Optimistic Modeling. This is my personal view of all this modeling. So mainly I think that it's like a...
Maybe.
Yeah, it's three pillars as always, but main is a theory. You always need to understand what to model. If you just use some software and try to think that machine learning will give you all job, probably it will not come through. And I will try to explain for this few examples how theory will come in place. Personally, I'm a person from DFT and, as I said, DMFT, but Misha Kostinson was a theory guy, and of course we are old, we didn't still used to have this ML, but hopefully the young people will do the job. Good. Magnetism, why is so interesting, even up to now? I just make some point of view. There's a long-standing program in America, so-called critical materials. Criticals means that it's critically important to substitute it. So you know that one of the main, it's like this, one of the main magnetic materials from 80s is so-called neodymium iron bore, and it's contained neodymium. It's very rare earth, exists almost in China, and of course America spent a lot of money just to substitute this element, but to have the same properties. It was long program up to now. I didn't know if they succeed, but you know that this neodymium, this figure of merit for these materials is still the largest. And I thought, my grandkids is always like to play with these things which you cannot pull apart. So kids cannot, if you know. And of course, this magnetic is related to exchange interactions. This is one example that nowadays you could still calculate this all exchange parameters. But it's not only magnetic, but also superconducting magnets. So if you remember, go to Hamburg, to X-Field, this is all based on superconducting magnets. It's working on helium temperature. If you imagine 5 kilometers of this superconducting helium temperature, you understand. So if you find some substitution which work at least in nitrogen, so it's normal, you will be famous. So we are still living in Iron Age. Yeah? Iron is the main magnetic materials. So you know everything which we have, steel, iron, carbon. Iron as a main magnetic materials is a very special. So this it's almost most stable nuclear. If you go fusion from different sides, iron is in between. It's more stable because is a lot of irons in our universe. But not only this. So iron is crucially important for life. So this one example. I don't know if you know this HEMA. maybe some biologists. I like this very much, and I know that, first of all, it's a very complicated problem. So it's absorption of oxygen O2 molecules in our blood and transfer. So this is almost the main things. But binding of hemo-oxygen is this very cooperative effect. In one position is bind oxygen, and another goes out. And this hemo, the main, how it's called, working element is iron inside hemo. And to calculate or model this, you need, it's a really many-body, very complicated structure. So also maybe some modeling, iron has a lot of polymorphous structure. Maybe not everybody understands that it's only one element from transition metal which have BCC structure, and it's only due to magnetism. Zener was first, but there is also HCP, FCC, and also this epsilon phase, very rich phase diagram. Almost all our society based on this steel, which is iron carbon, is also very complicated phase diagram, good for maybe modeling. And again, if you increase by a few percent, I know that there is a lot of metallurgical industry, and if you increase some quality of this diagram by a few percent, you will be millionaire, so for sure. Good. Magnetism. So we know that iron, cobalt, nickel from these transition elements are mainly magnetic. In the middle of this D series, manganese and chromium is antiferromagnetic suddenly. Why? So we try to explain. But if you look at these magnetic materials, iron, cobalt, nickel, you know, almost Curie temperature here is 1,000, he's 1.5 approximately 1,000, nickel is 500,000. Why? So from optical properties, it looks very the same, yeah? Good, and it's almost oldest problem in the mankind, yeah? Almost 400 years before Christ, they already know this. Good, and also magnetism superconductivity, we will talk about this later, but if you look at the phase diagram of this famous cuprate, this high TC superconductivity, very close is all magnetic states. And it's not known if magnetism is compete or help superconductivity. And also laser is important. So there is this famous guy in Hamburg, Andrei Cavalieri, who just increase superconducting properties or decrease magnetism with using the light. Maybe another interesting thing, since Sir Kostya Novoselov is now president of Bremen University. You know, long time ago, we did nice work. So it was his idea. He said, let's calculate theoretically something which is two-dimensional and magnetic. And we just think and choose these materials, which is not working now, but similar things is already works, like transition metal, the chalcogenide and so on. But we did these numerical things in one layer, you see, and we found that it's ferromagnetic and discuss electronic structure. And it turns that this is the first theoretical paper on two-dimensional magnetic materials. So there are a lot of citations. Good. Starting to theory, maybe few citations. As Einstein said, everything should be made as simple as possible, but not simpler. So we will have a lot of formulas, but sorry for this. And Richard Feynman, even in his lecture, said that ferromagnetism presents a very interesting, beautiful challenge. Why this lodestone is magnetic? Why is so complicated problem to models? because if you think about, let's say, iron as atoms, it has multiplets, we all know. In crystal, you have a bands, but this transition metals are somehow in between. They have a local moments even above Curie temperature, so it's been correlated, localized, but also experimentally we know that these magnetic d electrons are itinerant. They just participate in transport. So this combination makes it very complicated. Starting from what is magnetism? So maybe you know that a few hundred years ago it was this famous theorem or that classical system cannot be magnetic. Yeah, and only after quantum mechanics. So Werner Heisenberg, this is his paper. It's really genius paper. He just said that magnetism, with this Heisenberg Hamiltonian base of magnetism, come only as a combination from this exchange interaction, which is quantum mechanical effect from Coulomb interaction, strong, because before they think that it's just dipole-dipole interaction, and this theorem of Van Leeuwen and Bohr, yeah, now I remember, said that in classical system cannot be magnetic. But in quantum mechanics, this combination of strong Coulomb interaction and Pauli principle. Pauli was 7 years in Hamburg, make a habilitation in Hamburg. And Pauli principle was in Hamburg, somewhere close to Reeperbahn. I can. So only this combination produces famous exchange integral, which is combination of Coulomb and exchange from this asymmetric properties of fermionic wave function. Then come another person, is John Slater, who said that no, it's not localized effect. We need electronic structure. How to understand this? He said that magnetism, you can understand the energy which comes from difference from ferromagnetic and antiferromagnetic configuration, yeah, and or half singlet triplet, so it's the same. So he says that first we need electronic structure, and magnetism is just small, tiny bit of this electronic structure. It was Slater idea. Then come another person, it's Phil Anderson, who said, no, magnetism is a correlated effect. And so if you do this Mickey Mouse model for Hubbard model, where you have hopping and Coulomb, local Coulomb interaction, at least this two-side model you can solve exactly. This was always some small problem of quantum mechanics too for students. So it's write many-body Hamiltonian, write triplet states and singlet states, and found that singlet is the ground states. And if you calculate the half of the difference, you calculate exchange interaction. But now it's negative. And it's called kinetic exchange, Anderson kinetic exchange, also a big step in the theory of magnetism. Good. Now we think how to do it all easier. So which come from local force. So if you do like a simple mean field, so you rotate spin, not do it quantum mechanically, then after simple calculation, you calculate the energy of this rotation of spin, and then it's getting out that there is also like a cosine structure, but parameter J is exactly the same. So now we see that, yeah, we can do this much easier and can do even intensity functional. So we use this magnetic force theorem. This comes from my boss in Max Planck when I come to Max Planck first, long time ago. He did this for density, and with Misha-Kuznetsov we generalize for magnetic system. Idea is very simple. If you write in density functional total energy, we all know that this is sum of a single particle, and then you have some Hartree terms, some derivative exchange correlation and minus. This we call the double count. But if you do a variation, that's what Ole Anderson proposed, then you know that exactly these two complicated terms cancel out. This self-consistent contribution of the first term and this double counting exactly cancel out, and you end up only with fixed potential variation of single particle energy. It's a very clever theorem. And you ended up with the change of density of states or green function. This object is very simple, good. We can make a very simple analytical formula for exchange interaction. But basic idea of all this is, again, like a Higgs mode. So first we need to form a local moment. It's exactly this very stiff so-called Higgs mode. As you form the local moment in electronic structure, then there is so-called Goldstone mode, some mode which is related with magnetic stiffness or spin wave spectrum. And this we can calculate analytically. Yeah? That's what we did a long time ago. Should be integral, so one. So, and we can analytically find exchange interaction as a product of these two green functions, up, down, and some scaling function. Was good a long time ago, and with this density of states, generalized density of states for all transition metal, we can calculate exchange as function of, let's say, Fermi level or different position in periodic. And then we see that end of the transition elements is ferromagnetic, but middle, because it's like a G square, there is some theorem that's in the middle of transition element, these things become negative, it's antiferromagnetic. So we can understand that. Formula is good. So recently, with the same idea, we wrote a review. If somebody is interested, there is this reference piece recently, not only with exchange interaction, but with Zelashinsky-Mori and all different things. With Ole Eriksson, this is important person nowadays. He is the head of Nobel Committee in Physics now. There is a lot of database or how it's called, open modeling packages which have now this exchange formulas as some small part. So I recommended this one. If somebody knows, is GPW. It's a Denmark production, very good, but they have also this linear response and exchange interaction. So of course, personally, I like this well-known Lichtenstein formula. For old professor is good. With this formula, we also, how it's called, analyze orbital contribution to this exchange because it's a green function. Green function has orbital indices. We can find all the orbital contribution for iron, cobalt, nickel, and chromium. So you see that chromium and manganese is almost negative exchange as function of distance, because formula is so simple, you could find immediately. Calculate only ferromagnetic states and obtain all exchange interaction for all distance. And it's also important, all this orbital contribution, because if you have complicated materials, you know that before everybody is based on this simple, like simple rule called Goodenough-Kanemaru. This is John Goodenough, met him, this guy who got a Nobel Prize for battery, lithium battery. But before he did this Goodenough-Kanemaru. But in modeling, we can do this now, just very simple way. Also, I don't know, Volker Heine, if you know, he was from Cambridge. He asked us to help to understand short range order above TC, so we can expand green function in the spin splitting, because if the temperature rise temperature, the spin splitting reduce, this delta reduce, and we can calculate the second terms, not only J you already know, negative in the middle, positive, but we can do even the derivative. And he was very happy. We did this paper also a long time ago, that we can understand short range order only because of this term above Curie temperature. Correlation effect now. So again, if you look at transition elements and even rare earths and actinides, they're all so-called strongly correlated materials. Why? Because effective Coulomb interaction for these transition elements is always larger than effective bandwidth. But all the music, interest in music, which we have, like GMR, ITC, heavy fermion, is all related with this transition element, so to model. But still, superconducting properties is very hard to model. Good. What is correlation effect, and why this simplified Hubbard model was famous? So if two electrons go close to each other, it has a strong repulsion, and they model this as just Hubbard parameter. And model is trivial if it's only one band, but up to now we cannot solve this. On the lattice, two-dimensional lattice, we cannot solve Hubbard model. But there is a simplified scheme. Theory come to the power. And I don't know if you know, but if you don't know, 1 minute of explanation called very powerful theory appeared called a dynamical means field theory. So name is not very good. So, but idea is nice. So if you have lattice with all local Coulomb strong correlation effect, you need to find, so idea is to find the best local approximation. So local approximation means that self-energy is local. So if it's local, it's clear that it will be a functional of local green function. So you have lattice green function, you sum over Brillouin zone, get the local green function, and then find some effective model still that locally you have strong interaction, but the rest is so-called Gaussian. So you integrated Gaussian action. This is this formula, and you get effective so-called impurity model. So one correlated site in the bus of free fermion. But this model we can solve exactly. We cannot solve exactly Hubbard model in lattice. I will explain you why. But we can solve this model. And this is so-called impurity solver. As soon as you solve this impurity solver, you calculate the new self-energy locally and then put it back here and do and do self-consistent cycle. This is called dynamical mental cycle. There are a lot of impurity solver, Monte Carlo exact diagonalization, so on. And idea come to Antoine George and Gabi Cotler first. Antoine is now, because of this DMFT, is now head of theory group in New York center called CCQ of theoretical physics. It's called Simon, I don't know if you know, Simon Center. So it's a Chern-Simon. It's this Simon. He died last year probably. But probably due to machine learning, very similar things. He started to do some what's called business in New York and got about $20 billion. And he spent half of this to this foundation. Okay, coming back to magnetism. In the magnetism, in the theory of magnetism, there is three different historically theory. One was Stoner. Stoner is if you do DFT and try to calculate temperature where magnetic moment disappear. That's what you'll do. So you start from ferromagnetic ground states for iron, you try to increase temperature, this magnetic moment will be smaller, 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 and then suddenly it's zero. But this gives a TC which is 5 times larger than the realistic TC. And Heisenberg, we already discussed, it's just a quantum spin model, which is also not described. And what is more a realistic model is so-called Hubbard model, where your moment can change, but also is a disorder. Yeah, this is some kind of more realistic model. And then using this model and combination of density functional with this dynamical mean field theory, at least we can understand magnetism. So it was a big collaboration between different groups, also in Yekaterinburg. So it's good. So what we can do, we can just, this is different approximation, if it's a full Coulomb interaction or not full, because it's 5 orbital system. But nowadays, we can really calculate high temperature properties of this magnetic material. This experimental iron, and then you see, as function of temperature, we can quite good obtain Curie temperature, both in iron and nickel. So you see, it's already starting to be 1,000 here and 500 or something. So we can understand. We can also understand electronic structure, high spectral properties of this transition metal at high temperatures. So this is spectral function, and the dots are experimental RPS point. So you see, it's a very good agreement, and also we can understand or model why this majority and minority spin up and spin down bands are so different. So you see, it has a strong self-energy effect only for majority, but not for minority. Don't have time to explain why. And finite temperature density of states. So nickel is very important. I don't know, from experimental point of view. So there is these 3 properties which you cannot describe in a simple density function, DFT. So the bands are 30% narrow as LDA or DFT. There is this spin splitting is 50% smaller that we also can produce in DMFT, but also many body effect. There is this, for nickel, there is this famous resonance minus 6 eV, which you see in photo emission, you see also in DMFT, but you don't see in density function. And maybe last point, also this transformation, we can also understand using this DMFT more elaborate approach, mainly start from Leonov. Ivan Leonov is now in Yekaterinburg, Institute of Metal Physics. So only include, so if you start from just from density functional, you see a lot of instability of phonons and so. But using DMFT, you could understand phononic structure and also this transition BCC, FCC. Good. Now let's go to superconductivity. It's even more complicated problems. It's 40 years after discovery of high TC superconductivity. So it's this cuprate, which is very close to magnetic ground states, antiferromagnetic. So if you put 50% of hole doping, you get superconductivity at maximum 160 Kelvin. So, by the way, still the absolute record is this mercury compound. And I think it was from Moscow University, a group of Antipov, as I remember. I collaborated a lot with Andrei Antipov, who was the son of this Antipov. He is now in quantum Google in Santa Barbara, also doing a lot of quantum modeling. There is a lot of ideas. What is the mechanism? So up to now, nobody can understand the mechanism of superconductivity in cuprate. 40 years gone. Somebody said that, of course, Coulomb interaction is important. Somebody said, no, this magnetism in J is important, extended Van Hoff singularity, and multi-orbital things. So many different things. So why it's so complicated? Let me explain you. So you see, the model is very simple at the end. And it's realistic because I said that in Max Planck, together with Ole Anderson, so a long time, quarter of century ago, we start to analyze electronic structure of these cuprates and find that density functional theory, which is very good for Fermi surface, for IPCA, can be described. So nowadays, of course, you will do Wannier construction and obtain, but long time ago, we did almost by hands, from full band to some 8-band model. But Fermi level for metallic states is cross only one band, which is combination of D states of copper, yeah, and P states of all oxygen. So this is somehow wave function which corresponds to this valence band, which is important for superconductivity. It's only one band which crosses Fermi source. But chemistry or density functional theory said that there is interesting effect. So you see this Van Hoff singularity push drastically down, not in the half of the band. This means that not only hopping, which is T, like here, but also this T prime is very important. And T prime is negative over T, and it's 30%. So good. Now we said, wow, you have single band, T and T prime, very simple. We can solve this model exactly. Yeah, you have two-dimensional lattice. Of course, Hubbard model is quantum. You have U at each side, and we know how to solve this. It's a quantum Monte Carlo. It's the best place, maybe. If students, you have students, maybe a few words how you can solve this Hubbard model. Because this is hopping, electrons can hop, but also you have locally Coulomb interaction, yeah, U, which is many body. Yeah, you see, you have n up and n down, n squared. You cannot solve this. Yeah. This term you could solve. It's like a band structure, but correlation you cannot solve. So you do a trick, and the trick comes from Hirsch, Hubbard-Stratonovich transformation. By the way, it's also interesting. It's Jorge Hirsch, which not many people like, or people who has a big Hirsch index like it. It's a guy who invents this Hirsch index, Jorge Hirsch. So you have in this theoretical jargon, you make a square root of these terms, yeah? You make transformation, very interesting transformation. So you see here, it's all exponential because it's action formalism. You have this Coulomb interaction and up and down. There's some simple terms. And you could prove that you could exactly rewrite this using some auxiliary field, spin up and down. It's exact. So students can prove this in 5 minutes because it's a quantum operator. N can be, N up or N down can be 0 or 1. So there is only 4 combinations of this here and here. And you could prove, prove this all 4 different cases, this works. If both are 1 or 0 is almost trivial, but if one is 1 and another is 0, then you get this formula for this parameter, strength. Right? As soon as you do this Haber-Sarastonovich transformation, you could calculate this action. It's 1 electron effectively, and you get the partition function of this exponent of quadratic action is a determinant of this green function. That's it. So you have the answer. So Monte Carlo, you do Monte Carlo and this auxiliary spin and calculate determinant of green function. But it's determinant. Monte Carlo is good, you need a probability, but determinant can be positive or negative. This is the idea of the so-called negative sign problem. So it's a sign problem. It's a sign problem which hurt us to understand high TC superconductivity. So somebody is laughing really on us. Why? Because if the system is half-filled here, there is no sign problem. Jorge Hirsch proves that this determinant is always positive, it's square. But if you dope the system for this 15%, then the sign becomes 0 and it exponentially becomes 0 as function of inverse temperature, this Coulomb interaction, and number of sites in your simulation cell. So you cannot simulate. Of course, there is another group from Nikolai Prokofiev that said it's not sign problem, but sign blessing, but they still cannot. There is this so-called diagrammatic Monte Carlo, didn't have time to discuss, but they still cannot understand this two-dimensional superconductivity. What to do? And then come theory for modeling. So Misha Kuznetsov always asks me, can we, if you can calculate, this is chemical potential, which defined you whole doping, yeah? So here, half-fill case, we can do numerical exact simulation. Can we just shift perturbatively and get to this point where the chemical potential is order of 2, hopping, and here locate all these high TC properties. So we try hard and say that, yes, we can shift. This is a nice idea to modeling. So we call this super perturbation, dual Fermi Monte Carlo. So we have reference system, which we can solve. Mu is equal to 0, it's half filled, you see. And no T prime. Remember, I saw that for cuprate, T prime is important, 30% of T. But we cannot put it here because T prime break particle Hall symmetry and also produce a sign problem. But okay, what we can do, so our reference system is a half filled, no T prime. And it's insulator. It's exactly this antiferromagnetic insulator, parent compound. And then we try to shift mu and introduce T prime. How we can do this in model? It's called strong coupling perturbation. I will not, of course, say, but it's some diagrammatic things. You have perturbation, which is one electron. Mu is one electron part, and T prime is also electron part. But you have a correlated vertices. Up to now, we use only first term. There is a lot of theoreticians which do this strong coupling, but mainly driving force was Alexei Rubtsov. He's from Quantum Center in Moscow. So we did this, and it's inside Monte Carlo. So we start from our reference system, which is insulator, and but also non-trivial. It's correlated insulator. You have here Hubbard band, so-called related with this big U. You have also Slater, antiferromagnetic states, and it's blue is our starting point. And red is when we shift chemical potential, introduce this T prime. So you see what we did, we shift this to this peak. And suddenly this peak goes close to Fermi level, become extremely sharp. I will explain you why. It's very good for superconductivity when you have some big states near the Fermi level, but this Hubbard band just almost stay the same. And moreover, we can understand now superconductivity. On parallel to this, our perturbation, we can also introduce some superconducting field and try to understand the response of our system to this superconducting field, D wave. And then this is our first order perturbation in Monte Carlo. And then we can calculate the normal green function as function of K, this Brillouin zone, and anomalous, this Garkov green function, which is related with the delta. And then you see it's very untrivial properties. It's not pure. First of all, it's almost like D wave. So order parameters is he is positive, he is negative, he is positive. It's a D wave, no question. But the maximum is not at so-called at nodal point. And if you compare with experiments, so this is our Garkov green function, that the maximum is not at pi 0. And if you look at this review article of cuprate superconductivity, it's a Fermi surface, and they see a two different gap. So here and here, it's exactly at these 2 points. The gap is not superconducting. They say that it's a pseudo gap. It's a big gap. It stays with the temperature. It's even increase. And superconducting gap is also somewhere only in between. Here is 0 by symmetry because it's a nodal D wave, but maximum is not here, somewhere here. And only this superconducting gap reduces function of temperature and with 100 Kelvin. And we can start to see this physics. So we are quite happy with this complicated modeling. Also, maybe ARPES, especially some ARPES, now we can see how the spectrum function looks like, or transfer for undoped system. It's mode insulator. So you see it's insulated at Fermi level. This is gap, but also you see a lot of this modeness states. But as soon as you doped with the hole here and introduce T prime, so this band drastically changed. It become almost undispersive. And we know that undispersive band is also good for superconductivity. It's a lot of nowadays modeling of flat band and superconductivity, all twisted bilayer graphene and so on. So it become very flat. It's good for superconductivity. And there's also a lot of stuff, this many body stuff. And then here you have a small D wave gap. If you look at this D wave gap as function of doping, then you see like a dome structure with a maximum at 15%, which is also good. We can understand. But if the T prime is 0, then we cannot see this effect. So T prime is incredibly important. electronic structure and density functional theory can understand this physics of cuprate superconductor. Good. So we have a very simple summary. So what we discuss how to calculate the main properties of magnetic materials, exchange interaction and density functional, how to explain magnetic properties in this DFT plus DMFT. And we did the first small step to understand high-TC superconductivity in D-wave using this so-called dual fermi, strong coupling perturbation inside lattice Monte Carlo. So my collaborator is, as I said, Misha Kosnetson. 50 years we know each other from first university years. And then Losha Rubtsov, I said, this is a genius guy. Definitely, he designed one of the best impurity solvers, so-called continuous time Monte Carlo, but also the strong coupling perturbation. And nowadays, Zhenya Stepanov, who is in Paris, in École Polytechnique, he just helped us with superconductivity. So thank you for attending.